Right, there's a lot of confusion about Coriolis Effect, and doing a little video here to add to that confusion. I was watching one of Jeranism's videos. Love the videos, mate. I watched your video and then I went and looked at this original video, and I thought exactly the same as you. That does not make sense. So if it turns to the east when you're going north, then you're telling me it's going to turn to the west if you're going south, which seems counter to and independent of the rotation and the spinning of the globe. Indeed it is. It's nothing to do with rotation. There's no rotation in the Coriolis effect, and we'll see why. We'll have a look into that. So this is a video, this guy Jeremy Winter's product specialist, and this is bandied about a lot as a proof of the Coriolis effect being a proof of a rotating globe. It'll be thrown about in the comments sections. It's like, you're an idiot, this video, case closed, Coriolis effect, Earth is round.
Kind of just explain the Coriolis effect in layman's terms. The Coriolis effect is the effect that when the bullet leaves the barrel of the gun, it is actually leaving the surface of the Earth. So as the bullet leaves the barrel of the gun, the Earth is still rotating, and the bullet is not rotating with the Earth. So the Earth will actually rotate out from underneath. As the Earth rotates, it actually rotates from the west to the east. So what that's going to do to our targets is if you're shooting west, your target's going to rotate up and towards us, which is going to cause the bullets to hit lower. And if you're
so that's the Coriolis effect. I mean, it's not really an effect, and it's not really Coriolis effect either, is it? It's just, I mean, that doesn't give any explanation as to why storm systems turn. He's just basically saying that the bullet and the Earth are travelling separately and independently in their own frames, and therefore if you fire towards the spin, the Earth is going to rise up and meet the bullet. If you fire with the spin, the Earth's going to drop away.
Facing east, the target's going to be dropping and slightly moving away, which is going to cause the hits to be higher. Now,
just what? So, I mean, yeah. Now, if it's true, if what this guy says is absolutely physically true, then yeah, that is a pretty good proof that the Earth is a globe and that it is spinning. But in order for that to be true, so you should get maximum negative Coriolis effect due west, maximum positive Coriolis effect due east, and then you should get, if you're heading north, you should get a deviation to the left. If you're heading south, you should get a deviation to the right. That's according to this guy. Now, so this is like everybody's first stop for Coriolis effect, and so it's clearly bullshit. It clearly is not right at all.
So first, let's say that we want to go from here to an airport in China. Okay, are you with me? So concentrate now. Let's say that this is the Earth, and now let's assume that it is turning. If we take a flight from China, you say the Earth is turning, right? So if the plane stops in midair, wouldn't China come to it? Am I right? China should come to the plane. If the Earth revolves the other way, then the plane could not ever catch China, no matter how long it flies. Since China is revolving, you'd never get there. And this proves that the Earth is fixed.
There's a video here, lecture Coriolis effect. It's an academic approach to Coriolis effect. So I thought, well, okay, this will explain it. This will finish it.
we know, however, that if you go up...
They've got the speed at the equator going around 24,000 miles in 24 hours, 1,000 miles an hour. Halfway up at 60 degrees, you're at 500 miles an hour, and at the poles, you're at virtually zero. That's
now, by the way, there's not like differential rotation on the planet. The fact, and you're in Quito, Ecuador, which you know is right on the equator. And let's say that you've got a package that you want to send. And let's say that that package needs to be delivered up here to Nova Scotia, which we will say is approximately 60 degrees north latitude. Let's say that you've got a big slingshot. And this big slingshot has the capability of sending your package from Ecuador to Nova Scotia. So we want to send the package on the slingshot in that general direction. Okay, here's the thing. Let's say that it takes 1 hour for our package to go from Ecuador to Nova Scotia. 1 hour. Here's where it gets a little bit tricky. After 1 hour of time, this person on the equator is going to have traveled 1,000 miles to the east. Did everybody see that? Because remember, if you're standing here in the equator, you're ripping around the planet at 1,000 miles per hour. So after 1 hour, you have gone 1,000 miles. Make sense? If, however, you're in Nova Scotia, after 1 hour, you've gone 500 miles. Make sense? Okay. Let's say then, for sake of argument, that we send our package from Quito, Ecuador to Nova Scotia. The package leaves Quito. Not only does it have a velocity going to the north, but it also has a velocity going to the east because of Earth's rotation. As a matter of fact, when you release that slingshot and you release that package, not only is it going north, but it's also going east. So the true path that the package takes is this. And after 1 hour of time, the package is way over here. But after 1 hour of time, Nova Scotia is right there. So take a look at the path of the package took. It veered to the right. That is the Coriolis effect.
What he's saying is that this veers to the right. In the northern hemisphere, this maths gives you a turn to the right.
Anywhere on the planet, the results are going to be the same. Objects traveling in the northern hemisphere get veered to the right. Objects traveling in the southern hemisphere get veered to the left, always of initial motion.
Except it doesn't. So the first thing, it doesn't turn to the right. The direction is still heading due north. It just lands sooner than the latitudes that are further north.
This dude didn't pick up this big package and say, I'm going to throw it to the east with a ton of force. Absolutely not. He didn't do it at all. It's just the Earth's rotation. And so the Earth's rotation has taken the package to the east.
If an object moves north, then it's going to deflect to the right. So if the target was the blue cross there, and you set course for that blue cross, you calculate it without Coriolis, you're going to end up in front of it. You're going to deflect to the right, or not turn to the right, but deflect to the right. The course being dragged to the right rather than turning. Now, the only reason that that occurs is because of the difference in latitudes. So what happens if you travel on the same latitudes? Then surely there is no Coriolis effect. You throw your fire catapult off and it hits the intended target pretty much bang on, which is absolutely contrary to the sniper expert earlier. He was directly telling us that east and west, you are going to have problems. I'd only spent a short time investigating Coriolis effect, and already I was monumentally confused. And this was the source of my confusion. There are clearly two different things being described here. One is this conservation of angular momentum, which only applies apparently due to differences in latitude, and the other one is the sniper and his bullets with their east and west. So one's only affecting east and west, and one's only affecting north and south. Very confusing. Well, I then came across this video on YouTube, Sniper 101 Coriolis Effect on rifle bullets. Thought, you know, here's another professional who's going to be able to explain this, and not only explain it but demonstrate it physically as well. And if these guys are saying that this stuff exists and is real, then, you know, that needs to be looked at.
Howdy, Rex here. We're going to attempt to explain another thing you're going to have to be adjusting for at extreme long ranges, and that's Coriolis Effect.
Now, this guy does give some very good graphical descriptions and explanations of how the Coriolis force behaves and acts. And it's the same, it's the exact same basic premise and the same maths as the lecture.
Let's take a look at both of these. So this can affect your bullet both up and, you know, up and down, and also from left to right. The horizontal Coriolis correction, okay, that's a deflection that is the same irrespective of the direction of fire. So your right and left Coriolis correction is not going to matter which direction your rifle is pointed on a compass, okay? When you're shooting long-range rifles in the northern hemisphere, it's always going to deflect your point of impact to the right. So you're going to have to adjust left to counteract that. And an interesting thing to note is that it's actually true for your horizontal corrections. Any direction you're shooting, it doesn't matter if it's west or east, it's going to be the same amount of horizontal Coriolis correction, and it's going to be independent of direction. And that's the reason for that is the Earth is not a perfect flat surface that's moving uniformly. It's a sphere, and it's moving in kind of a weird way. You know, like we said down here, it's moving different in the curvature. It's going to actually, so that Coriolis force is always going to be to the right. So I can be shooting east or west, and your your horizontal deflection is always going to be to the right in the northern hemisphere. Now, if you're in the southern hemisphere, your Coriolis deflection is going to be to the left, because, you know, the Earth is shaped like this. If you just visualize it, it'll be easy to comprehend.
What? Okay, to quote Jeranism, timeout or technical foul, because he finished with a flourish there of stuff that suddenly didn't make sense, and we'd done so well. And is that a scientific explanation? Is that a grammatical sentence?
And that's the reason for that is the Earth is not a perfect flat surface that's moving uniformly. It's a sphere, and it's moving in kind of a weird way. You know, like we said down here, it's moving different in the curvature. It's going to actually, so that Coriolis force is always going to be to the right.
What was that? I mean, I've analysed this. I can't even call it a sentence. It's just garbled nonsense. It doesn't make any sense whatsoever. There's no explanation in there. This is an excerpt from, it's from a website, and it states that it's from Encyclopedia Britannica. Now here's the crux. The Coriolis effect is most apparent in the path of an object moving longitudinally. So a path moving north to south, south to north, changing your latitude. And that fits with the maths example. And that fits with this Rex's examples. They both tally, and they both use the same maths. They both use conservation of angular momentum, and they both state that if you move north, you're deflected to the right, and if you move south, you're deflected to the right. Thus, if a cannon were fired northward from a point on the equator, the projectile would land to the east of its due north path. We know this. This is we've covered that. So we've done this to death. We know that now. The difference in latitude gives you difference in distance travelled in the same time, therefore it's travelled further to the right. They then tag this line on the back, on the end. An exactly similar displacement occurs if the projectile is fired in any direction. It correlates with what Rex said there.
An interesting thing to note is that it's actually true for your horizontal corrections, any direction you're shooting.
I mean, what's going on here? The Encyclopedia Britannica has just gone glazed-eyed and mumbling and stuttering incoherent sentences like Rex there, and just said an exactly similar displacement occurs if the projectile is fired in any direction. Given no explanation why, no demonstration.
And the reason for that is the Earth is not a perfect flat surface that's moving uniformly. It's a sphere, and it's moving in kind of a weird way. You know, like we said down here, it's moving different in the curvature. It's going to actually...
This is not science. So far, if we have a summary of the laws of Coriolis as we've been able to determine them, there are 3 laws or rules. So we have 3 deviations of Coriolis. We have north-south horizontal, east-west horizontal, and east-west vertical. One thing we have barely looked at is which one of these 3 deviations of Coriolis effect are responsible for the weather.
See, it goes around in a great big circle, and that's what happens on the Earth. Now there's one more thing. The Earth is spinning, so the wind starts spinning. That's why wind comes from all different directions. Wind is wild.
Whoa, just hang on a minute there, Bill. Bill Nye, you're one of science's most famous poster boys. What was that?
See, it goes around in a great big circle.
Yeah, that's fine. So, low pressure to high pressure. Good, okay.
And that's what happens on the Earth. Now there's one more thing. The Earth is spinning, so the wind starts spinning. That's why wind comes from all different directions. The Earth is spinning, so the wind starts spinning. That's why wind comes from all different directions.
If the winds are moving north, then they deflect to the right. But if the angle, if the effect is lessened as the angle becomes shallower, so the effect becomes 0 when you're travelling on the same latitude, it has to be. I can't see any other way to interpret that lecture, the maths in that lecture. So the winds wouldn't circulate, they would stop once they got to be horizontal. And in fact, if they did circulate on this model, deflecting to the right, deflecting to the right, deflecting to the right, that's a clockwise rotation. And we're told constantly that it's anti-clockwise in the north and deflecting to the right.
The high pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air...
Right, so I went to this website, earth.nullschool.net, where you can play with these globes of weather patterns, atmosphere and the oceans, and you can play with lots of different projections as well. I was just looking for, well, those 2 things, the 2 things that seem to go hand in hand with the explanations so far on Coriolis effect, and that is northern hemisphere deflects to the right, and also weather systems turn anti-clockwise. Now, looking at this sort of western half and the North Atlantic there's around Iceland and Greenland turning anti-clockwise, but in that area, everything that's turning anti-clockwise, all the movement is deflected to the left. So that's contrary to Coriolis effect. Over here, so in the mid-Atlantic, I've got the same thing. Systems that are moving anti-clockwise are they're deflecting to the left. There is a system there right in the middle of the Atlantic which is rotating clockwise, and everything is deflecting to the right. Yeah, if you look down here as well. So those systems are rotating clockwise, but rotating to the right. So they're correctly rotating clockwise according to the theory, but they're rotating to the right, which is contrary. Then there is a system there off the coast of South Africa and Madagascar, which is rotating anti-clockwise, but it's deflecting to the left. We're seeing a pattern here.
In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise.
You know, I'm not just being awkward and obtuse on purpose. This is a website, you can go and check it out. It's supposed to be real. You know, this is what they say. So this is why this isn't science, because the theory that they're talking doesn't seem to hold to any kind of practical experiment. Here's the first practical experiment. Now, hopefully, you know, in these universities and learning institutions, as the years go on, they'll allow them to actually take their iPads and tablets into lectures with them. And so in the middle of a lecture, while the lecturer is telling you about clockwise and anti-clockwise and left and right spins and turns, you can bring this up and hold this up and say, here's a model that is just completely contradicting what you're saying. These systems seem to be moving to rules other than turning right in the northern hemisphere and anti-clockwise, and vice versa in the southern hemisphere. So that means that the Coriolis effect isn't playing out on weather systems. Otherwise, you can say the Coriolis effect turns either left or right in the northern hemisphere, or clockwise or anti-clockwise. And still, it's not a proof of the rotating globe. It's an illustration of a force at work. The internet has failed to answer this, really. There's very little of any substance online. Now, here's National Geographic. So winds blow across the earth from high pressure systems to low pressure systems. Okay, we've got that, and I can understand how that can create rolling systems in the way that the low and high pressures interact. The actual path of winds and of ocean currents are partly a result of the Coriolis effect. The key to the Coriolis effect lies in the Earth's rotation. The Earth rotates faster at the equator than it does at the poles. Okay, we're back to that example. This is the standard example because it does produce maths that actually works. Let's pretend you're standing at the equator, you want to throw a ball to your friend. So, you know, it's the same as catapulting a package, it's throwing a ball, and that's what most people use, throwing a ball. We kind of get that. Now, the apparent deflection is the Coriolis effect. The wind is like the ball, it appears to bend to the right in the northern hemisphere. But again, the example is talking about all the examples in this, all they do is give a due north and south example. See, all of these examples show very good, clear, understandable maths that gives a turn to the right, but they are all on due north and south examples. Nobody has given any demonstration of how this maths applies a turn to the right or deflection to the right if the projectile, the bullet, the parcel, the ball or whatever is thrown due east or due west. Where's the maths for that? There is no right deflection at all. It lessens as you go from 90 degrees to 0 degrees, and at 0 degrees it is 0 because you're on the same latitude. There's no difference. We've seen this throughout this video, and they keep mentioning it, saying that when you're firing east and west, yep, there's going to be a deflection, but they use this as the maths for it, and this maths does not apply. This website, Coriolis Effect, copyright 1996 by Dave Van Dommelen. This page was copied from ohiostate.edu. So far it's the best or the clearest actual explanation for the east-west deflection. Still, I think there's a lot of faith taken on this. This requires some explanation of centripetal acceleration. So centripetal acceleration is defined as the acceleration needed to keep an object moving in a circle at a particular radius. The basic effect of this is that if you go faster than allowed by your centripetal acceleration, you start to fly outward, and if you go slower, you drop inward. A good demonstration of this is to spin a ball attached to an elastic cord. Spin it fast and it goes outward, spin slower and it comes in. Objects moving east with the spin are moving faster, so they want to increase their radius, so they want to move outwards or upwards. However, gravity keeps objects from flying away, so it's not going to move upwards. It wants to deflect upwards, but it doesn't. It's prevented by gravity, which does directly contradict what the sniper was saying about the east-west, that it does deflect, but that's deflecting for a different reason. Right, so gravity stopping it from moving upwards. It would be travelling close to the ground, but now that it's travelling faster, it's going to move upwards. Because it's moving in a circle, it's going to move upwards and outwards from the circle, which means it's going to rise up from the ground. But gravity stops it from rising up from the ground. So therefore, instead of rising up from the ground, because gravity keeps it at roughly the same height, it will move to the right and get an increased latitude, or a latitude closer to the equator, and that's how it increases its radius. Okay, I'm kind of with that. I kind of get that, although I'm not convinced. So this projectile has beaten gravity in its motion, but then Coriolis has overridden gravity. The other way is westward bound objects. So yeah, so for the eastbound objects, gravity keeps the object from flying away. The ground stops things from falling straight to the axis if it's moving west. So if it's moving west, it wants to drop down. So most objects will be confined to a few mile layer thick at the surface. While they can rise and fall some, the best way to change their radius is to deflect north or south. So we've introduced gravity and then we've taken it away. In one direction, gravity is winning, and gravity is keeping the object from rising up, and therefore instead of rising up, it moves up the latitudes. Now going the other way, the object wants to fall towards the ground. If gravity is what is acting on the object that's moving east, why isn't gravity working on the object that's moving west and pulling that down towards the ground? But it's not. Westward bound objects, instead of skipping off the ground, they move to a tighter radius, to a higher latitude further away from the equator. That's how it reduces its radius. Why is that easier for the westbound object? Why isn't just succumbing to gravity and falling to the ground the easiest method? How does it overcome gravity and move to the north? That's perplexing. And also, according to both snipers, shooting east or west does produce fall or ride. So do we get both effects combined, shooting east and west? According to the second sniper, you do, because he's got calculations that show that. Got calculations that need to be done to shoot east and west, and they give two rates of change, horizontal and vertical. So if the vertical is playing on this, the objects are moving towards the Earth or away from the Earth, depending on how the planet is turning underneath it. So if an object is moving due north, and we have to correct for Coriolis for that, why is the planet also not rushing up from the left of the object if it's moving north, or rushing up from the right of the object if it's moving south? So surely what you've gained by conservation of angular momentum going north, you've also lost some, because the planet is also now revolving left to right under your feet. And going south, wouldn't an object have more right deflection, because as well as what is provided by conservation of angular momentum, the Earth also during the time of its journey is passing by from left to right. So I wonder how this relates to and affects like intercontinental ballistic missiles. How would you aim? Surely they would have had to have fired them off in a very different deflected direction for it to actually go over the poles and hit the country on the other side. Because if you fired it straight across the poles, wouldn't it almost land back at you? So that's a bit of a problem. There's no real mention of Coriolis effect being taken into account. There is mention of gravitational anomalies and how the North Pole would affect the path of US and Soviet missiles. So there's no mention there of whether that's guided missiles or whether they're just fired. And what about the Earth's additional movement into this as well? So as well as the Earth spinning, we're also moving around the Sun at some tens of thousands kilometers an hour. So why isn't that factored into it? And also the Sun is moving, so we're not actually going round in a circular motion, we're spiraling, and we're spiraling at quite some rate as well. So these don't seem to come into play or affect it at all. Now this is where we enter into another one of the mystical realms of science, and that is relativity. So it'll all be blamed on relativity. And the fact is that your speed, your velocity is relative to the surface of the planet Earth only. But it's not, because in order for the conservation of angular momentum theory and maths to work, we have to be relative to the core of the planet, because it's relative to the poles, it's relative to what is stationary at zero, which is the poles.
Even if you were at home on your couch though, trying to be as still as possible, you are still traveling a lot of miles per second every second. You just traveled a really far distance in space. The question is, how fast are we moving? And it's far more difficult to answer than I thought, because there are so many moving parts. Speed is relative. You only feel it when it changes. So anyway, you're already going 1,000 miles an hour as a person by yourself. The Earth is traveling around the Sun once per year. It's a trip of 584 million miles. To get the Sun back to the exact same point in the sky every year, it has to go all the way around. That means the whole planet is flying at 66,667 miles an hour as a planet. planet on top of your 1,000 miles an hour. You get where we're going? Then zooming out further, we are all tied to the movement of the sun. The sun is flying through our galaxy with all of its planets tucked into its gravity. Scientists determined the sun is moving toward other stars at around 45,000 miles per hour. We're also moving up relative to the galactic disk at about 15,700 miles an hour. We're moving approximately 550,000 miles per hour as a solar system. You'd think that might be far enough, but we are not done yet, because you, the planet, the solar system are all moving, and so is the whole galaxy. Our galaxy is headed toward the Andromeda galaxy at a pretty good clip. Numbers vary, but a recent 2013 Space.com piece clocked us at about 252,000 miles per hour. Again, with the three-dimensional thinking, the Milky Way is also moving toward the constellation Hydra at about 1.3 million miles per hour, and toward Virgo at about half that. So overall, the Milky Way might be traveling as fast as 2.237 million miles an hour. Another sidebar, by the way, the further away from you that you get, the more difficult it gets to measure your actual speed, because you're just moving a little bit, but the galaxy is moving 2.2 million miles an hour. The reason we use constellations and other galaxies to measure this is the same reason we use trees and mountains here on Earth to gauge distance. They are large and far enough away that they become a point of reference. We can measure our speed relative to theirs, but of course all of those stars and galaxies are also moving. And Andromeda, the galaxy, is moving, and the stars of the constellation Hydra, which is one of the constellations we measure against, is moving. Everything is moving.
Our speed, if you're at the equator, the 1,000 miles an hour is 1,000 miles an hour around the center. It's not 1,000 miles an hour through space, because we've got multiple additional rotational vectors to add on to that as well.
Your 1,000 miles an hour, plus Earth's 66,000 miles an hour, plus our system's 550,000 miles an hour, plus the galaxy's 2.237 million miles an hour.
I guess onto relativity, they're adding gravity, so you're relative to whatever is your closest, as it were, gravity well. But then we've got the moon. So the moon is pulling the tides and the oceans around. So it seems it's pulling the oceans around, but it's not apparently affecting the rest of the weather. And that's the only aspect of the moon's gravity that does. So if the moon's gravity is affecting the tides, then where's the relative framework for the spinning of the Earth and for Coriolis? When you enter this realm of travelling through space and relativity and gravity, it gets really, really difficult to imagine. And sort of on from this, what about satellites? So if a satellite is launched and it's in close Earth object, it stays relative to the Earth and it's pulled along, I take it, in the Earth's gravitational wake. If that's the case, shouldn't it be dragged along? Why does it keep its same circular path? And the satellites that are further out, how are they keeping up with the Earth moving around the Sun and the Sun moving through space? So again, I guess this is relativity and gravity, in that you stay in whatever relative gravitational well, and then that's what all your kind of frames of reference are.
The reason you're not clinging to the ground with fright right now is because, again, speed is relative. You are not feeling it because we're all on this supersonic journey jet together. Us and all the stars in the galaxy.
But to me, it doesn't make a lot of sense. And it needs people who are better at maths and better at creating visualizations to really look into this.